Okay. We have spoken about the solar system and all the planets in the solar system. We described the beautiful voyages of Voyager and how magnificent the outer planets are and how we might see planets in other solar systems. You know, it's but now it's time to, the rest of this course is not going to talk about planets, that's it. We're going to now speak about stars and how stars are made, how stars make heavy elements, how everything works, how astronomers can, believe it or not, tell the age of stars. How do they do it? It seems magical. So that's what we want to cover. Wait a few minutes. Any questions on where we are or other things you want to ask? Everybody satisfied? How many people have seen in this course have seen things they really didn't expect to see, or you know, neat stuff? Yeah, it's kind of amazing. It's amazing what our universe shows us. You know, I have a tall order. I got to tell you about the entire universe outside the Earth, and it's a big place. The Earth is pretty big, and we know a lot about it, but the universe is really, really, really big. Who's seen the movie Contact? Right. Now remember, that was written by a scientist. The guy who wrote it, Carl Sagan, was no slouch. He is most famous for this television series, 15-part or so series that appeared on PBS in the 80s, I think. I don't think you've seen it, but I imagine it's available on someplace, web something. And he talks about beautiful structure of the universe, and it's a really good course. We should have another one like that, but they should just they could redo it, but they really should just do something, just to take away people's ignorance. All right, so the sun. Well, there's a picture of the sun. These pictures I'm going to show you are largely taken with satellite pictures or through special telescopes that image the sun. This is the image of the sun in a band that you don't see. You can see all these strange spots, a huge flare. This is a narrow band filter, and it shows it brilliantly shooting off these flares. That is strange. Okay, now, the sun is a thermonuclear bomb, sort of. And the sun has to allow protons to come together. Here is a proton, and here is a proton. And we know that if you take protons and push them together, they're both positively charged, and there's a strong repulsion between the two protons. They don't want to be together. They push themselves apart. So these two protons do not want to be together. The low speeds, the electromagnetic repulsion of the two protons is more than enough to ensure they won't come together. Now, protons obey. They go through a process that we call quantum tunneling. That process is very strange, and it's something that does not happen in classical dynamics. So suppose we say this is the energy surface. I'm going to draw energy this way. And we have a proton coming in with zero energy, or just a little bit more than zero. It's coming in like this. And it encounters a proton. So this proton hits another proton, and there's a barrier. Effectively, there's a barrier, and it looks like this. So the proton, here's a hill. The proton approaches the hill and immediately is repelled. After all, you take your bike and try to run up a hill, and you have to pedal in order to get up the hill. But it'll just turn around if you don't pedal hard enough. Now, that won't happen easily. But in quantum mechanics, the proton can leak through this barrier. If it does, it can enter a state of bound hydrogen 2. This can be bound hydrogen 2, and it's a lower energy than the original state. But it can't get in there unless it comes in with a high energy. At a low energy, it's going to be bounced back. But if the energy is very high, let's say it comes in here, then it's relatively easy for the proton to tunnel through the barrier. It's not as hard to do it. Now you can think of this as energy. Energy is temperature. When the temperature is low, two protons will never collide and go through a barrier. They won't do it. They're not moving fast enough. If the temperature is high, they will. All right, so that's the process. That's barrier penetration. This is a process that is possible in quantum mechanics. Quantum mechanics allows this to happen. It does not happen in classical physics. All right, so the barrier penetration allows the protons to get close together, and then they're so close together, the strong interaction takes over. Now, the strong interaction is something that holds the nucleus together. And you can think of the strong interaction as being Velcro. The proton has Velcro, and the other proton has the other sign Velcro, and they stick together, but only when they're close. You have to be real close, then Velcro takes over. That we'll call the strong interaction. Whereas the electromagnetic interaction is just like gravitation in the force law. The force is not confined to real narrow distances. And as the protons get closer and closer together, they're pushed apart continuously. And so that's what makes them do this, they bend. Okay, so the barrier penetration allows them to get together. Strong force then interacts. Here's barrier penetration. Blunk, it goes down, and it's made it through the barrier. Okay, now, it won't go, it's like a bump. You can't go through it with classical physics, but in quantum mechanics you can. That's it, words, what I just said. All right, so all right, when close enough, now the two protons get really close together, and then we have to change a proton to a neutron. Protons will go to neutrons. Here's a reaction. Neutron, this is a natural reaction that will occur. If you have free neutrons in the laboratory, got a pile of neutrons, in 20 minutes, the half-life of them says that in 20 minutes or so, half of them will spontaneously decay to proton, an electron, and a neutrino. Now, what the hell's a neutrino? Now, notice that the proton and electron, positive 1, minus 1, they balance. So there's no net charge on the right-hand side. The neutron has no net charge on the left-hand side. What is this neutrino? Well, this was a surprise. when it was discovered in the 30s, 1930s. Okay. Now, anytime you have an interaction that involves neutrinos, it's called a weak interaction as opposed to the strong interaction. That's a separate nuclear force. Physicists discovered this and realized it is a different type of force. You haven't seen it classically, and so it's kind of strange. Okay, neutrinos were first suggested in 1930. Wolfgang Pauli, who's the guy who made up the exclusion principle, he could not understand how the energy was not conserved in the decay of a neutron, because this thing has certain energy, these have an energy, this has an energy too. They never could see this neutrino. It just flew away. And so he named it neutrino, which means little neutron in Italian. He's an Italian physicist. And so neutrino is a little neutron. It's not really a neutron at all, but he called it little neutron. So it's stuck. Okay, that's the name it has. A little neutron. All right, so what happens then is you have a proton and a neutron. And we know that protons and neutrons are the necessity to have deuterium. Deuterium is the isotope of hydrogen. Hydrogen is just one proton. Deuterium is a proton and a neutron. And when they are put together, it's called deuterium. All right? So now, this happens, all these bang together, the strong force, energy is conserved in this reaction because it's conserved by the fact that the particles are moving fast. That's how you conserve it. All right? And these particles are moving fast, and that helps conserve the energy. All right, so the quantities that must be conserved, the electric charge has to be conserved, the total number of baryons, this has to be conserved, P and N. You can think of it as a number of baryons to be a quantum number of the reaction. That has to be a conserved quantity. And the total number of leptons. This is E and neutrino are lepton number +1. An electron, and this is electron minus, that's normal electron and neutrino. And there are anti-electrons that are called positrons, and antineutrinos that are called antineutrinos. Good enough. And they have lepton number +1. So those are conserved quantities. That is to say, we have generated E plus, let's see. All right. This is what happens in the sun. All right. So the reaction is basically that you take proton this is in multiple stages. Proton goes to hydrogen 2. Remember, that's the notation. Hydrogen 2 means hydrogen with atomic weight or atomic number of 2. Atomic number in this case is protons and neutrons. And that it also releases a positron and a neutrino. Now the positron is of lepton number -1. The neutrino is lepton number +1. So that that gives a lepton number of 0 for the whole reaction. This has baryon number 1, 1, and here baryon number is 2. And so the baryon number is conserved in this reaction. So we've conserved the quantities in this reaction. Electric charge, here is 1, 1. 1 is here, 1 is there. So we conserved electric charge in the reaction. So these are the elements of the chemical reaction. This is chemistry, just like the chemistry you learned, only it's chemistry on a nuclear level. All right. Now, you probably haven't taken any nuclear. This is called nuclear chemistry. Have any of you studied nuclear chemistry? All right. If you if you're in a chemistry department, you'll study this sort of stuff. This is now the domain of chemistry. Okay. Now, first of all, this reaction, P plus P, goes to H2 plus neutrinos. The neutrino immediately escapes the sun. Because neutrinos have basically no cross-section to hitting anything, they just go out the sun. And it's amazing how they just go out. And very, very rare is there anything astrophysical that has neutrinos, traps the neutrinos. So this is all the way from the center of the sun. The neutrinos just work their way out, and nothing stops them. It's like the sun is invisible to them. And that's pretty incredible. That means, now this homework problem you have is to calculate the number of neutrinos per second that hits you when you stand in the sun, or you stand anywhere. Doesn't matter if you're in a building or not. The neutrinos are streaming out of the sun, and they go right through you. How many neutrinos per second are going through you? I want you to calculate that. And the problem shows you how to do that. It's more than one. Let's put it that way. It's a pretty large number. It's pretty amazing. All right. So, and then this is called it is a slow interaction because it depends on the weak interaction. That is, the neutrino has to transform to a proton, a positron, and a neutrino. That doesn't happen that often. So it's a slow interaction, and it's a slow process. It's very much slower than if it weren't necessary. All right, so then we still haven't made all the energy possible. You've now got deuterium in the center of the sun. So step one, two protons make a deuterium atom. They make a positron and a neutrino. And here's deuterium. The positron collides with an antipositron, an electron, that happens to be floating around in the sun. The electron and positron collide, and they turn into gamma rays. The gamma rays are released when that happens. All right, so now, next you have these neutrino. This deuteron collides with a proton and makes helium-3. Normally, helium is 4. All right, you guys know that? Did you learn that in chemistry? All right, helium atom normally has 4, it has a weight of 4. But here we make something of weight of 1, or weight of 3, I'm sorry. But we take a third step in the reaction is you take 2 of these helium-3 atoms, slam them together, and it makes helium-4 plus 2 neutrons. 2 protons. All right, so here was 1, here was 1. They slam together, make 2. And a few of the odd particles are ejected from there. So this cycle has... all right, so what happens? The net result is that you take 4 hydrogen atoms and you slam into 1 helium atom, and you get a lot of energy from the form of the particles moving away at high speed. So this is how nuclear fusion works in the center of the sun. This is something worked out. Physicists realized this in the 1930s. All right? So that is the energy source of everything we do. You think of coal and oil. Are they energy sources? Well, they're secondary energy sources because they're leftover remnants of solar power. Solar power made the plants, which were compressed and later made the coal and oil. But they all originated from solar power. Solar power is everything. All right, so the result is this complicated cycle that makes energy from the protons in the nuclear star, in the star. Now, the star, in order for that to happen, the first thing you have to do is overcome the barrier penetration. You can't expect electrons or protons moving that are way down here to barrier penetrate. It has to be up here. They'll barrier penetrate. And what that means is that only in the core of the sun, only in the core is the temperature hot enough, is the sun hot enough to make the reaction work. All right. Now, suppose we want to replicate this on the Earth. I want to build a nuclear reactor. And mankind is trying to build a nuclear reactor. The best example of that is the laser reactor that's happening in Livermore. Okay, now what does that do? How does it work? All right, so if you're going to make a fusion reactor, you start with helium-2 instead of hydrogen. Don't take hydrogen atoms because then you have to depend on the weak interaction, and that's very slow. So skip that. Start off with hydrogen-2. Where do we find hydrogen-2? Anybody? If I wanted to go out and get a mine of hydrogen-2, where would I find it? Sorry? I can't hear you. The ocean. Because hydrogen-2 is a naturally occurring isotope. We'll talk about why it occurs. It's a naturally occurring isotope at about 1 part in 10 to the 5th. So every time you pick up water molecules, about a part of 10 to the 5th of them contains deuterium. Well, overall, this whole ocean, that's a hell of a lot of deuterium. That is an enormous amount. So that's cool. You can mine it. You can get it. You can extract it easily. All right? Now you have to, the next thing is you've got to confine this hot plasma. You get it real hot. You turn it into a plasma. That means the electrons are stripped off from the atom. So you've got this hydrogen, too. And you have to make it hot enough to stay together and slam together and make it all fine. Now, unfortunately, the temperature in the center of the sun, well, fortunately for us, the temperature in the center of the sun is 30 million degrees Kelvin. How the hell do you get something that will sustain 30 million degrees? You cannot build it out of material. You can't build it out of walls because the wall will dissolve instantly. After all, metal melts at temperatures of order 5,000 and 10,000 degrees. Well, that's only off by a factor of 1,000. Nothing to it. What the hell do you do? Well, obviously, this deuterium has to be confined somehow, has to be held away from the walls. You cannot allow it to touch a wall. Just won't do it. So and to do this takes a ton of money. So you got to find a rich benefactor who will fund you. The United States government has funded this for 40 years by now. And everybody, every time you ask them, when is this going to be ready? When can we build a nuclear reactor out of one of these things? When can we build it? And everybody always says, another 30 years. We'll tell you how to do it. They haven't been able to really do it yet. They have an idea for doing it with this huge laser system in Livermore. All right, what is it going to do? All right. So, first of all, let me see if you understand what we're talking about. Take out your cards and tell me, when fusion occurs, What is fusing? What particles are fusing? All right, talk about it to your neighbor. And then show me a card. You're not talking loud enough. Let's have some discussion here.
I don't have people to talk to.
What?
I don't have people to talk to.
Oh, well, okay. Talk to them. Okay. Hold the cards so I can see them. All right, most of you have yellow. Yellow is right because the protons are fusing. The electrons aren't fusing. The neutrinos don't fuse. There's nothing to stick them together. But the protons are fusing. Now, all this fusion, of course, is very different from fission. The splitting of atoms, we're not talking about fission right now. We're talking only about fusion. Fusion reactors make a lot of sense. They don't make radioactive debris like, unfortunately, is contaminating Japan, where they had those fusion reactors were overcome by this gigantic tidal wave. Tidal wave, I'm told, was 30 feet high, and the reactors are fairly close to the ocean. 30-foot wave comes in off the ocean. They were prepared to keep away a 15-foot wave, but the 30-foot wave overcame it, washed into the reactors, flooded everything, killed the pumps, electrical pumps that were really necessary to run cooling liquid through the reactor, keeping it cool. And as a consequence, it was not cooled and got hot enough to melt. So it was a real mess. Okay, so these reactions of fusion, you say, well, we don't have any of those problems. So let's build it. The problem is it's so damn hard to do it. All right, so protons are fusing. All right, now, astronomers are curious to know what happens when the sun runs out of hydrogen, because this is occurring in the center of the sun, and it's burning the hydrogen, and the hydrogen is being converted to helium. So the sun over time is changing. Eventually, it will run out of hydrogen. When it runs out of hydrogen, what happens? What happens to the sun? That will be another 5 billion years. Yes? Yes, but let's see what we really mean by that. What happens in detail, okay? You're right. Okay, so why does that happen? Okay, this whole process now is called the red giant phase of a star. We'll see later why it's called a red giant. This is because, as was said, the star expands enormously. It's really quite amazing what a star does after this. The star will eventually expand to the radius of the Earth from the sun. Now that will fry us, and we'll become a crispy critter. 5 billion years from now, we had better, 5 billion years is so long. Who can plan for? You can't even plan for 5 years. 5 billion years is probably a bit much to plan for. But anyhow, at that point, if we're still around, you'll have to have some sort of rocket ship to get people away from the Earth. Anyhow, okay, we'll worry about that later. All right, first, the process is called triple alpha process. Is the hydrogen is going to be gone, and the star is then going to try to burn the helium. Helium doesn't want to burn. It burns a little bit, but it's very hard to make it burn, so let's see what is involved. Now, basically, it's called triple alpha because you're going to have to take 3 of these alpha particles. An alpha particle, alpha rays, beta rays, gamma rays, is an old name given to the radioactive particles that came off from the radionuclei, were seen to give off these rays, and they were just called alpha, beta, gamma when nobody had any idea what they are. So they're alpha rays. The alpha rays turn out to be alpha particles. All right, and alpha particle is a nucleus of helium. Beta rays turn out to be protons. Turn out to be electrons. And gamma rays turn out to be gamma rays. The name's the same, gamma rays, electromagnetic radiation. Okay, so what happens, first of all, since you can't have a reaction that has helium, 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 three ingredients cannot mix like that. You can't do that. In chemistry, it's always two reactants make something else. You never have 3 reactants. You can try it, but the probability of hitting 3 reactants is very, very small. So the way the process works is first, helium makes beryllium. That's beryllium-8. Beryllium-7 is the stable element of beryllium. Beryllium-8 is incredibly radioactive, and it splits up in very short time. It's about less than a microsecond. I don't know exactly what it is. But it's not stable. You can't make it to stay for a long time. So it reacts, and it's there for a short time. It's a miracle. The fine structure constant has to be within incredible that this reaction occurs. It's amazing that it happens, because if it didn't happen, we wouldn't be here. We depend on this reaction for life. Why? Why? Is because the next thing that happens is beryllium-8 and helium-4 makes carbon. That's how all the carbon is made, how all the carbon in you is made. And that reaction occurs immediately after the sun runs out of fuel. As soon as it runs out of fuel. All right? Now, then the carbon picks up another alpha particle, and it makes oxygen-16. Runs away. All right, now these reactions, if you say, how is this carbon and helium going to react? Now, the barrier penetration the height of this barrier is dependent on the reactions. This barrier was drawn for protons hitting protons. That's charge of 1 against charge of 1. Here, the next thing we're talking about is beryllium hitting carbon. Beryllium has charge of 4. Carbon has charge of 2. So the product of them together gives a force that's 8 times larger than the one for the first proton-proton reactor. So it's going to have a barrier that goes way up here, and then down here, and something like this. It's going to have a huge barrier. It's like you're trying to make it through a gigantic wall of a prison. where the walls are high. You're just not going to make it. Unless your energy is high enough. So the energy down here, corresponding to 10 or 30 million degrees, is nothing. Let's raise the temperature. Oh, way up here. If you get the temperature hot enough, then you'll get a particle leaking through that. How hot are we talking about? It's not 10 million degrees. It's more like 200 million degrees. 200 million degrees. 200 million degrees. That's huge compared to the 10 million degrees or so that is necessary, that was there for the sun. How does a star manage to have energies that are so high? How in the world can it do that? Anybody? What happens? It brings up the most important part of the course. I want you to, this really matters. Okay, so, all right, let's talk about this a little bit more. So what happens is reactions, here this carbon making oxygen. This requires incredibly high temperature, and people have worked out that the highest you can go is 1.4 solar masses. It won't work beyond there. All right, and that's the maximum the star can weigh and still be making these processes go. Now, all this occurs, this beryllium and helium burn, but I haven't said how much energy they give off. It turns out they don't give off much energy. So the star gets incredibly hot, and all it does is gives a little energy. I mean, the energy is not enough to last 10 billion years, which our sun will hold. It'll last 10 million years. That's it. 1,000,000 times shorter. No, 1,000 times shorter. You know, there isn't much fuel. You burned all the fuel you had, and now you just got the little pittance, and you get a little energy out of it. But that's it. Now, that makes the whole, because it's so little fuel, very modest amount of fuel, that means that all the reactants burn up, and the whole process has to go through it again. Something happens. The star lasts in this phase only, instead of 10 billion years, it's going to last 10 million years. 10 million years in my business is nothing. 10 million years is, it's all compared to the age of the star it could have been. A star could have been 10 billion, and it's 10 million, it's 1,000 times shorter. That's nothing at all for astronomers. Now, it seems like a long time, but it's really not. And we'll see how short a time it is as we go on. Okay, so this reaction can occur and will occur in the sun once it runs out of hydrogen. All right, now the next issue is what happens to the high energy particles, say the neutrinos, and the high energy photons that the star emits. Right from the center, here's half the star. Right from the center, the star emits a photon which walks out in something called a random walk. A random walk is like a drunk near a telephone pole. Takes a step, he wanders, he's really drunk, he goes off in some different direction, takes a step, takes a step, takes a step, takes a step. He keeps taking steps. Eventually he gets his distance from the lamppost grows because he's taken enough steps. All right? Eventually the star, the photon, in this case the photon, gets out of the star. But it has taken a long time to do it. Now, this is the energy transfer from the center of the sun. So the energy starts off as a high-energy photon, the gamma rays emitted by the reactors. And then the photons they diffuse. That's what I mean when I said this drunken walk is called diffusion. And the photon diffuses out of the star. It diffuses, and it keeps colliding with atoms or other material. It collides, collide. It actually turns out to walk about a millimeter, and then it collides. It's got a million miles to go, a millimeter at a time. So it takes a while to get out. Even though it's traveling at the speed of light, it takes 10 to the 5th years for this hot photon to walk out of the sun. 10 to the 5th years. Well, it's a very long time, and it's been walking slowly. All right, so they suffer a collision every 10th of a centimeter or every millimeter, as all these collisions occur, the photon degrades in energy. It doesn't have is born in the center of the sun an extremely high energy photon, and it comes out the surface of the sun as a modest temperature of 5,000 degrees or 5,800 degrees is the temperature it has when it emerges from the surface. So it has degraded in energy all the way. All right, so this rate of diffusion interior to the star is what regulates the heat leakage. So it's a slow process to get the heat out. And the combination of the radiation from the surface and the power emitted in the center causes the total. You can balance the two when they're equal. It turns out the total power of the sun is some 10 to the 26 watts. 10 to 26 watts. How much do you consume every day? The problem I asked you to calculate in the beginning of the semester, what's the average consumption? Oh, you're typically burning a few light bulbs. Light bulbs about 60 watts. So 100 watts. About that's how much energy you're emitting. How much are you radiating? Just the warmth of you is giving off energy. What is that? Anybody remember what that is? Is it something like 50 watts or 4 to 30 watts? I don't know. How warm are you compared to a light bulb? It's a little hard to tell because the light bulb is all concentrated in a point. But it's of order 30 watts, say that. Okay? The sun puts out somewhat larger energy. That's what it does. Okay. Now, this process is part of a war that happens in every self-gravitating system that we will talk about in the course. The self-gravitation means that there is pressure, all this pressure on this red thing. The pressure is pushing the star together. You've got a star weighs a lot, and it's pushing it all together. What is resisting the pressure? The pressure is resisted by the energy generated by the sun. The energy generated by the sun is generated, the gravity, the gravity is the weight of the star. All the weight of the star pushes on you because of the huge amount of gravity. And it won't let go. Pushes it together. It's making the sun as small as possible. Why doesn't the sun shrink? It's because of its internal pressure. Your balloon, if you blew the balloon up higher, the pressure is higher and the balloon expands more. If you don't have the balloon blown up, You let the pressure off, the balloon shrinks. The pressure is what holds the sun up. The pressure is what holds everything up. What is it that holds the Earth together? The Earth is held together by the huge amount of gravity it generates. Why doesn't the Earth shrink? Anybody? Why doesn't the Earth shrink? There's a lot of, yes? It's a solid. And why does a solid resist shrinking? You can't compress it, right? Why can't you compress it? It turns out that it's a pressure that it exerts. If you didn't have that pressure, if you squeezed it in a way with no pressure, that means strip the electrons out. Strip the electrons, you can collapse it. Okay. All right. Now I told you about Jupiter. Jupiter, Saturn, all the giant planets turn out to give off a lot of energy. They give off twice as much energy as they receive from the sun. How do they do that? It's because they're leaking energy. They're sort of a failed star, and the energy comes out of the surface of the star, and that's energy from its original formation. The formation has given it energy and is squeezing it out. Okay, now let's think of this. An ember of wood. If you squeeze an ember of wood, an ember of wood, a burning flame. A burning flame gives off heat, and then as it gets quiet, it turns black, and it doesn't give off heat anymore. Now, a self-gravitating star, on the other hand, is very different. Self-gravitating ball of gas, no source of energy. Suppose you imagine the sun has no source of energy, and you want to, or anything is self-gravitating, the Earth and whatnot. As you shrink it, it heats up. And that's completely opposite of a classical ember, an ember of coal. Why does it heat up? Why does the sun heat up? And you can think of the following. If you throw a ball up in the air, or you start with a ball up here, and you let it come down, and it hits the ground, the energy of the ball in this, all this kinetic energy up here, or the potential energy of the ball up here, has been transferred to motion energy, kinetic energy, and then it splats on the ground and turns to heat energy. So imagine the Earth is covered in something, the whole Earth is covered in balls, and they let go. All right? Then the Earth gets a little warmer. So the Earth getting warmer is very much like the self-gravity of a classical gas with no source of energy. If it shrinks, it gets hotter, and to let it cool down, you expand it. Shrinking gets hotter, cool down, it gets larger, it gets colder. Now, how do you understand that in a different way? Maybe you can understand that by thinking of Einstein's idea where a ball rolls down the hill and is rolling into a new potential, and the potential makes it move faster. It moves faster, according to Kepler's laws, moves faster when it's in close than it does further out. Everything is the same. Why does that work? It's because the energy released, it releases energy when it comes down, sinks into the center. Similarly, if you've got out here, you've got a planet here, and a planet further out. Earth moves around at a certain speed. Jupiter moves around at a slower speed. If you want Jupiter to spin faster, just bring it down into the center of the sun, and then it will spin faster. And the energy of the Jupiter looks like it's higher when you're in closer. It's not really higher, but it looks like it. It's just that the energy, the kinetic energy, which can hold the system up, has increased. So this is very different than anything you've thought of before. I want you to realize how different this is. The objects, as they're big, are cold, and as they shrink, they're hot. And that is because of the negative heat capacity, it's called, of the self-gravitating ball. All right, so the sun heats up as it shrinks. All right. The stability of these thermal reactors, it's a thermal reactor we have making the sunlight, and it has its own regulator on it. A regulator, what is a regulator of a steam engine? For example, if you make a pressure cooker at home, pressure cooker usually has on it a heavy weighted, a metal ball on the top of it that is a release valve for it. So, because otherwise the pressure cooker could explode. All right? What is the release valve doing? It is releasing energy if the energy gets high enough. The energy pushes the release valve up and then escapes. There's all types of, what are regulators that you know on machinery that you've ever worked with? I can't think what they are in modern cars. I don't know. All right, anyhow, a lot of things need them because otherwise it's hard to control it. Okay. The sun has a size which allows the thermonuclear generated power in the center of the sun to get out. If somehow this thing started generating more energy, this nuclear reactor generated more energy, what would the sun do? It would get larger. The sun would get larger for a few moments, and that would allow the energy to escape. All right. Now, if you want to know what the temperature and luminosity in the interior of a star, you have to solve the equations that it satisfies. These equations are differential equations. They're very well known, and they have been solved. They've been solved for 100 years, or nearly 100 years. The solution says that the center of the sun is a little more than 10 to the 7th degrees. The outer surface of the sun is 10 to a couple thousand degrees. Here is density. The density in the center of the sun is 100 grams per cubic centimeter. And the density on the outside is very low. 100 grams per cubic centimeter. Remember that water is 1 gram per cubic centimeter. But the center of the sun is much, much denser. Now, how the hell do we know that? Because, in fact, the data is in the yellow curve, and the models are the black dotted lines. The model fits the data spectacularly well. That says astrophysicists know how to construct the model of the sun. This is all worked out mathematically. If you want to read how to do it, pick up an undergraduate text on stellar interiors. It's all worked out. But if you're going to be an astro major, you'll learn how to do this. But this is not considered a big deal. These are well known to do this. Okay, so when we say the star has this constitution in the center, we really mean it. We've solved these equations very carefully, and this was the solution. All right, so now, here let me just ask a question again. What kind of radiation shines out of the center of the sun? Suppose you took all the material off the sun, everything goes, and just looked at the core. What kind of radiation do you see from the core? Is it visible? Red, blue, ultraviolet, gamma rays? Hold up a paper and tell me. Yeah, talk to your neighbor to decide what it is. Talk, 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 talk.
I actually do not have I don't think I have the...
Hold them all up.
Okay.
Because that's sort of white if you hold them all up.
Okay, fair enough.
They can get one over there.
Might as well do that.
Yeah. All right. Is it visible light? No. It's not red, blue, or ultraviolet. Ultraviolet is hot light, but real hot light is gamma rays. The white card. Most people got that. Gamma rays come out from the center of the sun, and gamma rays can be deadly to us. They can penetrate our skin and give us cancer, but they're heavily shielded by the entire sun on top of them, so no problem. Gamma rays are what is released. Remember that the photons are degraded as they walk out from the sun. All right, now the thermostat in the sun is a very interesting object, and this is how a thermostat would work. Thermostat, suppose, oops, back up. All right, let's start here. Suppose the sun here got these reactions going off in the center of the sun, and suppose the temperature goes up. If the temperature goes up, that means this level is going to go up. And it's going to go up to the point where the barrier penetration is going to be easier. And that means a lot more barrier penetrations occur. And that means the energy generated by the rate of fusion goes up. So you raise the temperature in the center, and the fusion reactor is burning more. What does it do? Generates the fusion. The fusion means that there is more pressure generated by that. The gravity is about the same before. The pressure pushes the thing out. It's like you blow up the balloon. The pressure pushes it out until it comes into equilibrium. It wants to be in equilibrium. So that is, the gravity has to balance the pressure. But that will occur when it's expanded a bit. The gravity has compressed the core, heating it, and it results in increased pressure. All right, so on the other hand, if you went the other way and you decrease the core temperature, you just suddenly decrease the temperature, they decrease this, that means the barrier penetration is weaker and less energy is generated. Less pressure is exerted, the pressure is not as strong, and the gravity is stronger, and the gravity pushes the star together, and it makes it a smaller star. All right? But it's in equilibrium. So it's adjusting its size a little bit to adjust for temperature variations. It's a little wobbly. In that sense, the feedback is stable. You can adjust lots of temperature a fair amount, and the sun's the same. It just adjusts itself and prevents it from exploding. What happens in a nuclear reactor is that it gets hotter and hotter and hotter and hotter until the pressure way overcomes nuclear bomb. There's no gravity to stop it, and the pressure pushes, and blows up in a very short time. I don't know, microsecond time. The whole thing blows up. It won't blow up in the sun because the weight of the sun is so enormous it pushes it together. That's the real problem with this nuclear fusion idea. It'd be nice to have nuclear fusion, and a little place you have a little system that makes energy out of nuclear fusion. The problem is that it needs a lot of mass to hold it together, to hold that whole fusion reactor together. That's called a star. Okay? You want a fusion reactor? Here, take a star, and you've got a fusion reactor. Okay? So when you build, if you're talking about, well, hell, let's just make something that uses fusion to take the energy, why don't you just make solar collector? After all, that uses the results of fusion. It's a hell of a lot easier than these other systems. So, okay, enough of that. All right, now, let's go on to something else that's very, very strange. The sun turns out to be a crazy, crazy object. Particular. It doesn't rotate as a solid body like the Earth. The equator rotates faster than the poles. And it's really differential. It's incredible. It takes 25 days. The sun rotates around in 25 days at the equator. But to rotate around at the pole takes 30 days. Wow, that's really weird. Can you imagine that on the Earth? The Earth, the equator rotates fast, and the sun's poles don't rotate that fast? Whew. Why does it do that? It's not really held together in the same way. It's not a solid object. It doesn't have to rotate at the same rate. And because it's not solid, it doesn't. It just doesn't. All right. So what does it do? All right, it has magnetic effects that are incredibly neat. Here is, if you look at the sun in detail, here is what you see. Okay, this is what the sun looks like. The sun has this sunspot and these little specks of corn. Don't they look like corn? Corn in, corn kernels. All right, they're called granules, but it sure looks like corn. All right, now, the granulation is, those cells are bubbling cells, and I will show you what I mean by that. They really are bubbling on the solar surface. All right, the sunspots, the temperature of the sunspot is a little cooler than the rest of the sun, and we'll see why in a moment. Okay, so let's blow up a sunspot. Here is a sunspot taken in time-lapse photography, and you see a sunspot moves. All the little thing moves with it. Pretty neat. So that is changing on a daily basis. Now you can't see this when you look at the sun, of course. This was a picture taken over a couple weeks. But the sunspot does change. All right, now, it also gives magnetic fields that are incredible. The magnetic fields are seen as outlining, they're the white things. All right, they are white prominences, and these prominences blow off the sun all the time. That's, again, very beautiful. So these prominences are there. The other stuff is there. The energy transport comes up this way, bubbling up and then going down, up and down, up and down, up and down, and gives rise to these granules. All right, so that's called convection when it does that. Something's heated here, comes up, and then lets go. Convection. And what happens is the photons come down here. They're absorbed. They're not scattered simply the way happens lower in the sun. They're absorbed by the material. The material gets hot, and it comes up. All right, so the bottom of the zone is heated. Hot gas rises to the top. Cooler gas sinks to the bottom. And this is exactly the same effect of boiling water in a pan. When you heat a pan of water, the pan is very hot, and it bubbles up the stuff, the bottom. It makes the material come up, and it turns over. Come up and turns over. Come up and turns over. The sun is boiling. That's in a word. It's boiling. Okay, the energy is brought to the surface by this process of bulk motions moving, and that is called convection. So there are three types of energy transport that I think I learned about this in the 9th grade or something. There is radiation, there's conduction, and there is convection. Did you learn this? Somehow this is a big deal in the 9th grade to learn this. Did you learn this ever? Or they cut that chapter out? Energy transport and whatever. They never saw that? Well, you're familiar with it. Radiation from the sun, conduction from a hot metal pan. The handle is hot. That's conduction. And convection is the boiling of water. The sun does all three of them. It's heat transport. Very simple. Okay, now here is a beautiful simulation of the solar convection cell. So if you look at one spot, it's not fixed. These spots move. They're wandering around. Okay? And that is, let me do that again. All right, well, here they are again. These are the hot spots. The red is the cold spots of sinking material. All right. Solar convection cell. That's what it looks like. The sun is boiling, 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 all the time. Really beautiful. All right, so let's look at this again. Now, these are pictures taken with a spacecraft. All right, so the sun is erupting. Remember, this takes 25 days to rotate entirely, so this is sped up. Here, it's boiling once in a while, bubbling here. A little flare. The sun's not too active right now. Now, the issue is that the sunspots occur in pairs. There's one here goes down this way, one here goes down this way. The pairs are allowing the sunspot to have a positive pole and negative pole. Just like the Earth has a north pole and a south pole, the pairs of spots are that north and south pole. And they rotate, of course, with the sun. All right. They come and go over an 11-year cycle. Why does it do that? Does that because of internal complications in the sun. The Earth has a cycle too. Anybody know how long it takes the Earth to cycle? We have had, for as long as anybody can remember, a magnetic field, but the magnetic field has wandered. It's not always fixed at a certain point. What is the period for the magnetic field of the Earth? All right, well, let me go ahead on that. All right, sunspots. Okay, sunspots are, by taking a spectrum of the sunspots, you can, these triple lines, 1, 2, 3, are due to magnetic field splitting, Zeeman effect. You know, who knows, ever heard of the Zeeman effect? If you study quantum mechanics, you'll know what it is. All right, anyhow, that's an indication of a magnetic field. Their spectra are split in 3, and that's evidence of strong magnetic fields on the sun. Yes? What's that? Yes. This dark is a spectral line, and here the spectral line is split in 3 because of what is called the Zeeman effect, and that has to do with the electron moving in the atom in a triplet state, L equals 1 state, which can have 3 electrons in it. But that's complicated. Let's forget that. Okay. Now here's what they look like. Got these granules, and you have a sunspot coming up and this way. So one side is positive, and it goes this way. All right, it just wanders over the sun. Here's flares. All right, these are X-ray pictures. The gas is trapped. The reason they're lit is the gas gets here, and the gas atoms, the protons and electrons, cannot cross the field lines. They go along the field lines, but they can't cross them, and they're trapped in them. But the magnetic field expands. All right, so this magnetic field gives some of the pressure and the temperatures a little lower where they emerge. That's all it is. It's not a big deal. All right, and so you observe this temperature of the sun at 5,800 degrees Kelvin. That's its whole temperature. But the temperature of a sunspot is 4,500 degrees. 4,500 degrees to 5,800 looks black because, comparison to 5,800, it is black. Remember that the luminosity goes as the 4th power of the temperature. So 5,800 over 4,500 to the 4th power is probably about 2, roughly. Okay, so the sunspots, if you look at it, this is twice as bright here as there. And that looks dark when you compare it. It's not dark in reality, but it looks dark. Okay. All right, so, okay, the reason is that less heat is transported to the surface. Photosphere is cooler. All right. And here is the magnetic fields. These are magnetic fields from the sun. It goes up and down. This is how many we're seeing, 1940 to 2000. Now, it's going to turn into a graph. It's going to curve. It's going to say, here is plotting, how much energy, ultraviolet radiation, comes from the sun. 10 to the 6th, 10 to the 7th, it was a lot. And then as you go into between sunspots, it falls. The ultraviolet radiation coming from the sun is a strong function of the number of sunspots. Okay, that's one thing you learn. Okay, now, there's something I want to talk next about, something called the Maunder minimum. The sunspots come and go in an 11-year cycle. They come and go. And there was a period when the sunspots were not going very well, 1700 to this area. There's no sunspots in here. The aurora were very quiet at that period. There was no aurora. Aurora means that there is active material flowing out of the sun. It typically flows with the sunspots. So if there's no sunspots, there won't be any aurora. All right. Now what happens? Now, okay, so the 11 years the sun has a solar maximum. What's the period for Earth to go through magnetic reversal? Anybody? 20 years? 200, 2,000, 20,000, 200,000? Anybody guess? Sorry? 20,000. Now, this turns out to be incredibly useful. Suppose there are certain types of rock that have magnetic crystals in them, and the magnetic crystals line up with the magnetic field. All right? And this is really beautiful. Well, I'm not going to draw it. If you go to the ocean, right near the huge split in the ocean floor, you can see alternate bands: up, north, south, north, south, north, south, north, and they're matched. What's going on? Well, they're telling you that's the history of the Earth. These bands are laid down as this Atlantic Ocean spreads out. As it spreads out, lava comes up from the center of the Earth, and then it deposits this stuff, and magnetic field is aligned with the field at that time. So it says the magnetic field was north, south, north, south. And remember that these magnetic field lines spread. The plate tectonics makes the ocean spread out. And so you can see the spreading just by looking at the floor of the ocean. It's most incredible. This was realized some time ago. All right, now, I want to talk about finally this. If the sunspots if you plot the sunspots as a function of time to 1900 and 1950, sunspots were not present in a while. They weren't present anywhere. Nothing showed. And what happened? This is a drawing of London. What are they doing? This is the Thames River. The Thames River was frozen solid. And they're cavorting on the river. They have a houseboat. They have these, they're walking on the river. They have all this, they're having a good time walking on the Thames River that's frozen. Similarly, at the same time, the Zuiderzee and all around Netherlands was frozen. The canals were frozen solid, frozen for people to walk on them, and they skated all across. Here are guys playing hockey, I guess, right here. Everybody else is skating. And so that's why the Dutch were famous skaters, because they could skate all around the canals. Now, who's been to London in the winter? Most of you haven't been to London. But London in the winter is nowhere near freezing. How about New York Harbor in the winter? It doesn't freeze. How about Valley Forge in the winter? You know, the terrible winter of Valley Forge when Washington trying to feed his men. It's in Pennsylvania. It's not that cold. They get some storms, but it's no big deal. Why? Here's a question that is literally not understood at present. Why is why is the weather so different during that period? The Earth was extremely cold when the sunspots were very low. Why? All right? Now, one last plot. Here is a plot that shows, what does that show? It shows the temperature of the Earth as a function of the age of the Earth. Now, this is dated back 500,000 years. From 500,000 years ago, the temperature it went like these variations. All right, and the carbon dioxide levels also had a similar oscillation to them. These are taken from ice in Antarctica, these measurements of temperature. The temperature of our period is this little speck here, right there. That's 10,000 years there. You note we're in a warm period. And more than 10,000 years ago, we were in a cold period when there was a lot of ice. There was tons of ice. Most of Canada was covered in ice. Ohio, where I'm from, was covered in ice. The Great Lakes were made out of those melting icebergs, huge glaciers. And 10,000 years ago, it got warmer. The Earth's temperature is not constant in time. That's one thing you learn. In spite of what Al Gore told you, that the Earth's temperature is very stable, it is not stable. It is not stable. And we can do something very dangerous. Here's a carbon dioxide level. And it's a part of something. You notice climbing, going straight up like it's never done in 500,000 years. And that's man-made. We're doing that. All right? And this is, here's carbon dioxide level relative to what it was 1850. And it's climbing, climbing, climbing. All right, the Earth's temperature has gone up 7/10 degrees in the last 50 years. But it's not a hockey puck. It's an oscillation, a dangerous oscillation that we've made. All right? He said it's like a hockey puck because you can extend this forever. But that's not true. You can extend it for a few thousand years, and then it really changes. Why does the Earth have these temperature variations on it? Why are they associated with the Maunder minimum? What the hell makes that happen? We're not going to say anything more. This is a mystery that is not understood at present. It's literally not understood. I can talk to somebody if you want to know. It's very complicated, but it's not understood. All right? All right, here's a question. Please answer this question, then you can go. All right. Suppose the sun turns off tomorrow. All right, what's going to happen to the Earth? We're going to have panic. Temperature, the sun will get lower, grow dimmer. Is that right? Because the Earth quickly freezes over. It would drift off into space. What is it? Just give me an answer here. I'm sorry we're a little late, but just quickly give me an answer to this. Anybody? Come on, I see one answer. Only one guy's answering. One. How about somebody else? 2, 3, 4, 5. Huh? What? Where's your cards? Blue. It's blue. Yes. We wouldn't even know it for thousands of years. Actually, we'd know it, but I'll tell you why. So, all right. So sun's pretty neat.
I think I didn't take
Yeah.
notes because I just like know
Yeah.
a lot of it.
Huh? Yeah. Could you move this move it in the corner? Okay. I'll see you next time.